All right. So this is about where we left off, right? We were having a look at the program for adding 31 and 32 and then doing 31 minus 32, right? That's what we were doing. And this is a program. Well, it's a program in its entirety, and you remember that this chunk of it was instructions, and this right here was data, right? That was the 31 and 32, okay, because those are the numbers we want to add. If I wanted to change the numbers, I could just go in and modify what's in here. All right, so, and remember, like, this is hex. But really the hex is, like, it's binary, right? Like, instead of writing 1E, I could have done 0001 1110, right? I could have wrote it in binary, but I've got it in hex here because it's a little easier. And the nice thing I like about hex is because it's 4 bits and 4 bits. Like, this is like the instruction, that's the operator, that's the operand. Operator, operand, so it's a little nice. And of course, we look at this and we know exactly what it means, right? We know this is obviously load A from RAM, load B from RAM, add, save, output, but unsigned, load, subtract, save, output, but signed. Of course, it's obvious, right? You look at those letters and you know exactly what the instructions mean, right? Obviously. This, by the way, if I didn't make it clear earlier, this is what we call like machine code. All right? We input zeros and ones, and it tells the computer to do something. There's instructions there. But, like, this is where, like, the rubber meets the road. This is where, like the machine code is where, like, the binary patterns that we can just put in a file get onto the hardware, and what actually runs on the hardware. I fear that the lookup table creates too much of a level of abstraction that you might miss the point that, remember, the lookup table is simply a stand-in for like a programmable logic array. We could make the hardware with gates and transistors to do like 0001 means go and do this. Like you were kind of doing in the lab yesterday, right? You were making the hardware for, well, when those two first bits were this, and the next bits were this, it means add. And when they change, it means a different operation. It means like a different instruction. So we can make we can do it a little bit more like physically, but we're kind of cheating a little bit. Not cheating, but you know what I mean. Like we're jumping on to a fairly abstract thing, the lookup table, which just is a map from inputs to outputs. But it's still all running on the hardware. So like I was saying, this is where the rubber really meets the road with the machine code. This is called machine code. Sure, it's in hex, but it's 01, 01, 11, 01, which really mean low voltages and high voltages that run through the circuitry to actually do the computation that we want. We were able to do this before, but we had to manually manipulate the control signals. Now the system can do it itself. What else did I want to say about this? And remember last time as well, we used these two memory addresses to store like the result of the sum and the result of the difference. And I wanted to make sure it was clear that, like, well, how come I didn't put them in? How come I didn't write them? Well, because the hardware will go and save to those RAM addresses at runtime. And think for a moment, like, here I'm saying load, like look at the line 2. Load into register A the contents of the address E, or 14, right? This line right here. It is really, I really wish I could like renumber these lines from like 0 to 15. I think that would be a little nicer, but whatever. It is what it is. Think for a moment, like, okay, this is programming. When we write programs to solve problems with something like machine code, We go about it the same way we write any code in any other language. The difference here is like, well, what can I do with that language? In Python, I could say print 31 plus 32, and it just does it. But there's a lot more steps involved on the actual machine code. Now, before the Python code actually runs on your computer, it gets like, there's a lot of steps, but traditionally, like, it gets compiled into machine code effectively that runs on the computer. So there's a translation method to go from your high-level language down to machine code that can actually run on your computer. All of you are using like an x86 architecture, right? So there's an instruction set for the architecture that you all are using, okay? It was created decades ago, and it's rather popular. x86. This is not x86. It's far simpler. But, you know, it's getting to be just as powerful, technically speaking. So when you write, like, C code, raise your hand if you've ever written C before. Okay? That's fine if you haven't. You don't have to feel bad. But if you write C, you compile that code, and it turns into the zeros and ones that write on your computer. It will turn into effectively this. Okay? All right? You write your code. You compile it to, here, let's see. I don't want the assembly. I don't want the actual. I don't know, like. I can't quite find what I'm looking for, but the point is, at the end of the day, it would look like something, it would turn into something that looks like this, okay? Your code. Now, obviously when you're writing in C, if I were to say like int a equals 5. No, let's say 31. Think about like what that means. Like what does that, now that we have some context about the hardware and what's running on the hardware, which we're going to talk a lot more about this, don't get me wrong. But I want to take a moment to make sure we have a sense of like, well, like what's going on there? All right, fine. 31. That's like putting 31 into here. But not quite, because A is a label. And somehow we need to keep track of the label. A references A is where the value that I care about, 31, is stored. So it's almost like, kind of like, oh, that would be like, okay, well, A, well, really, that's, okay, that's the number 31. This really here, that's like address E, right? Okay, so anytime I want to access, I need to know it's E. So it has to do a little bit more work. And also, like, it's typed, which is interesting because this isn't. And the type is more like, okay, when it comes to like displaying, when it comes to decoding the bit pattern that represents this, right? Because what's 31? 0, 0, 0, 1, 1, 1, 1, 0. 1, 1, 1, 1. There. Right? So that's, right? But, it's an integer. Oh, so that's, okay, that means 31. But if it was a character, that would mean something different, right? So this really isn't something we are managing here, the type. That's more on us. Now, our system can only really display integers anyway, so who cares? But, yeah. All right. So to go from something as simple as this to something like that, there's a lot of steps involved. All right, okay, since each line corresponds to a RAM address, each line should be filled. However, before runtime, the contents of address B, C, and D are not used, although C and D are. Okay. See right here? These are not used, right? But because like each line in this file goes into RAM, we should put something in there. I'm pretty sure with digital, actually, if we left these blanks, it would have put zeros in there. But, you know, put the zeros in there. So these lines are not used. At least they're not used until runtime. Maybe they're used at runtime, which we know they are. C and D are written to by the program. And also, because a halt exists, the address in address A, right here, these things could never actually be run, right? The program would stop. The program counter wouldn't move anymore. We can't fetch the next instruction, right? So it really doesn't actually matter what we put in there, but you know, if it's not supposed to be anything, put in nothing. 0, no up, whatever. Therefore, the contents of RAM don't matter, but you know, 0, whatever. So any questions about that? That was mostly review from 2 days ago. Yes?
So that code is specific to the system that we've designed it for?
Yes. It's not, it's more than that. It's specific to the system. So all of what we've done so far is like a part of the system. But remember how like we invented what the instructions mean? So it's dependent on what the instructions are, and the instructions are dependent on the system. So I guess there's a little bit, if we really wanted to get into the nuance there. But yes, you couldn't take this and tell it to run on your computer. Your computer would be like, what the hell's that? It wouldn't know. Now, mind you, you can take machine code for x86 and run it on your processor. Your processor's more than happy to do it. That's all it ever does, is run machine code for its hardware and instruction set. Does that answer your question? Yeah, so this is very specific for our stuff. We could change our hardware slightly, and it would require us to maybe update this. I'm thinking for the assignment, I'm going to actually have you go and change your instruction set a little bit. So you take what we have and you modify it, which might sound like a lot, but it shouldn't be, because you just take the code I gave you, modify it to modify the instructions, run it, load it into your lookup table, and then you're all set. All right, okay, yeah. Now, let's do a little bit of analysis of this code. We're not doing a computational complexity analysis, right? Like, what's the computational complexity of this? Well, knowing what the program is, it's constant time. It just runs and does some calculation. Nothing here depends on like an input size. So let's think of how much, like, what are the resources this program uses? Clock cycles, like time effectively, and space, RAM. So how much time does this program take, and how much space does this program take up? How many clock cycles, how much RAM? Well, how many clock cycles does the program take? There are, in fact, a total of 11 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? How many clock cycles does each instruction take, no matter what? 2? 4. Because it includes fetch, right? Yeah. So 4. So that means it takes a total of, what is that? Interesting. It takes a total of, that's very strange. But it's down there too. What did I do? By the way, if you're ever curious and you want to see the markdown for that, you can just load it up like this. I've just got an extra backtick for some reason. Well, that's easy to fix later. Anyways. So it takes a total of, if there's 11 instructions, each one takes 4 clock cycles. It's 44 clock cycles. Now, technically it's 43 because the system, the halt actually will not actually take 4 clock cycles, because on the 3rd clock cycle, it deactivates the clock, and it could never actually run that 4th microcode step of a halt. So if we really wanted to like get more specific, 43 clock cycles, technically, really. If you said 44 on a test type thing, I'd be like, yeah, fine, whatever. But if you want to get fancy, yeah, it's 43. Is it clear why it's 43? Halt deactivates the system as soon as that 3rd microcode runs, which is turn the halt, like stop the clock. So it can't actually do that 4th one. Because if that clock's off, the microcode counter won't be running, meaning nothing is running. Halt only requires 3 clock cycles, not a full 4, which is interesting. Now, can the program be adjusted to take fewer clock cycles? Right? We want to save time. Well, you remember, we talked about this last time. Remember how, like, okay, if I have A and B, the first instruction is load 31 into here. The next instruction is to load 32 into here. And then I add the result. And then I overwrite A to be 63. Right? That's what happens. 1, 2, 3. First 3 instructions do those 3 things. But once we get down to line 8, like if I want to now do the subtraction, 31 minus 32, I need to put 31 back into A. Just remember, A is an accumulator. It like overwrites its stuff. And then the next instruction, I reload 32 into B. That was entirely unnecessary. Now, you might say, like, yeah, obviously, okay, we can, we can get rid of that one instruction. We really don't need 3F. We don't need to reload 32 into B, right? But I want to make sure this is clear. When we are, okay, great. Okay, we saved that. Like, did we really save a lot? That's 4 clock cycles. Okay, how much? Well, that was 9.1% of the total amount of work that the system did. It's almost a 10% speed up. That's pretty good. But of course, what is the trade-off? Right? It cost me something. Maybe it didn't in your eyes, but there's always something nice about having very intentional code. Right? Where, what do I want to, like if I just showed you, if I ignored the first part of the program and I didn't have the load 32 in there, you might be like, what's in B? I don't know. Right? Like it requires someone to know more. Where if I very explicitly, okay, load that. It's very clear. The instructions become a little bit more self-explanatory, which is always really nice. However, that comes at a cost of like almost 10% of the runtime. Like there's a trade-off. Make the machine code more self-descriptive, or save time. Now, I've talked a lot, if you've had me in 161 or 162, I always try to make a point to talk about these trade-offs. And what do I say? What is computer code for? For humans. It's not for computers, it's for humans. But when I say that, I'm usually talking about, let me finish. Raise your hand if you remember. Okay, who's had me for 161 or 162? Do you remember me saying, like program, like code, computer code is for humans, not computers. But I also always finish this by saying what? I always say machine code is for machines. And that's machine code. So at this point, the machine code and what we're coding in is the same thing. Is my point clear? Like, the trade-off, the speed up, but we want our code to be self-descriptive, but clock cycles, how do we optimize this? There's a trade-off, but in this particular case, this is the machine code. We want to save time, we want to save resources. We get the luxury in high-level languages to write verbose code that's very self-descriptive because we have things like compilers that turn it into optimized machine code. So machine code tends to get very ugly for the sake of speed. First of all, you probably already think it's kind of ugly. Ugly in the sense that, what does this mean? Crap. Give me the lookup, give me the reference sheet so I can know what each letter means, right? So it's already hairy, but it gets even hairier because we try to do things like squeeze out everything we can out of our hardware. The high-level languages don't care about that because the compiler does that translation to the low-level language. Here, we don't have that luxury. So reloading the data 32 into B, we could cut that and save 9.1% of the runtime. It's kind of a big deal. Any questions about that? Or was that like painfully obvious? All right, it's neither. We already talked about this a little bit. What else could we do to actually reduce the total number of clock cycles? We talked about this before. But don't think program-wise. Don't limit yourself to thinking of the program. What could we do? Well, because we talked about it, and it might not be obvious because we talked about it, is we could, because we know several of these instructions don't really need that, they don't really need that fourth microcode. So maybe we can modify the system to like reset. Yeah? Like, let me show you what I mean. I'll just show you. Right here. This is the microcode counter. The microcode counter has a clear input signal. Actually, I'm curious, does the clear work on a clock pulse, or what does that say? Use as measurement, help. Clear. Synchronously resets the counter if 1 is set to 1. I'm guessing that means synchronized to the clock. Okay, perfect. So, I have the ability here, if this microcode counter goes 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, maybe there's a way I can say, like, okay, if I'm doing load direct, which only requires 3 clock cycles, maybe I can also reset the microcode counter to like save a clock cycle, right? So maybe the microcode, that would require another control signal though. Like, how could I possibly reset that? Well, I can have it so my microcode for load direct, maybe I can configure it in such a way, maybe this won't work, I don't know. Depends on the synchronization of the system. But maybe what I can do is I can say load direct is output from the instruction register, input into the A register, and restart the clock, restart this. So we don't waste that clock cycle. Let me try to make it clearer, because I'm seeing a lot of blank faces. We've got fetch 1, so this is clock cycle 0, 0, 0, microcode counter, really I mean, right? Fetch 2, and then 1, 0, we have, right? That's what we're doing. And then 1, 1 is nothing. There's nothing. So if I ever call this instruction, which is just one example of an instruction that only takes 3 steps, we do something, we do something, we do something, wasted clock cycle. Is it possible to say like, oh, and reset? Basically, so it doesn't go to 1, 1, but goes back to 0, 0. Thereby skipping this wasted clock cycle. Maybe we could do something like that. Maybe. But it would all depend on when the reset would really do this. Is that neat? Yeah? So that might be another way, by like changing the configuration of the system. Not so much the instructions, but we can maybe squeeze out a clock cycle in the hardware. By the design of the hardware, not with the program. Isn't that neat? How like a change in that, we can maybe even squeeze out a little bit more. We're not just optimizing our code, we're optimizing the hardware that the code runs on. which we never were able to do in like 161, 162, or 255. You can't change your hardware, but we can because we're inventing the hardware, which is pretty cool. Any questions about that idea? I don't know if it'll work. Maybe it won't. Maybe if I do a reset here, it messes up this instruction microcode. Or maybe the reset would actually just be like on the next clock cycle, thereby skipping this one, going back to 0. I don't know. We'll find out later. Any questions, thoughts, concerns, comments, anything? Happy, sad? Okay. All right, so that's the clock cycles. Now, this takes up 15 memory addresses in total. 11 instructions, 2 addresses with data, and more addresses are used at runtime, 2 more. So we have 11 instructions, 2, and then 2. We can reduce this down to 12. Remember, verbose code may be easy to understand, but maybe we really want to save RAM. Now, in this particular case, did we need to save RAM? Not really, because we had enough RAM to do our job. But, you know, if we've got bigger programs and we really do need to use all 16 memory addresses and our program needs 17, is there a way we can optimize it such that it can fit into 16? Right? So what can we do to reduce this? Well, first and foremost, we already talked about we really didn't need that second load 32 into B. If we get rid of that instruction, not only do we save a clock cycle, but we save a memory address. Sorry, 4 clock cycles and a memory address. So that's good. So we can already save something there. Great. Now, also, because of how I designed this, I saved 31 into C. Sorry, I saved the result of the addition into C, and I saved the result of the subtraction into D. But you know, I saved it into C, and then outputted C. And then I effectively, like, the next thing I wanted the system to do was output the result of the subtraction. So I didn't really need to keep storing the number 30, the result of the addition. Okay? I could have put 31 into I could have put 31 into address D, outputted address D, and then put I keep saying 31. I could put the result of the addition into address D, output it, and then put the result of the subtraction into address D, output it. I could have overwrote the 31 because I didn't need to actually keep it. So I could have saved a memory address there. But even more than that, if I really wanted to, I could have overwrote the values into F. Because I only needed to have F once to load it into here. Right? I needed to put 32 into B, and then it was fine. I didn't need to do anything with it. So I had 32 here, put it into B. Once I get that, I don't need this address anymore. This is just wasted space at this stage. So I can actually go and overwrite which was ever in here. So I could actually have saved the result of the addition into address F and the result of the subtraction in address F, thereby saving even more RAM. Is that clear? But this might feel a little funny to you, though, because, like, this was program code. I know this is data, but, like, a lot of people, like, let me put it this way. I could have stored the result of, now this is nasty, but it'll work. Pay attention, because this is weird. I could have stored the result, instead of saying 5C, I could have said 50. What would that mean? Save the result in address 0. But what would that do?
first instruction?
Yeah, it would overwrite the first instruction. Does that feel like a good idea? It's kind of weird. So let me put it this way. Does it matter for the system? No, because once that instruction, once the value in that memory address is used with how this program is written, I can't ever get back to it. So who cares? I can overwrite it. I don't need that instruction anymore. It's free space. I can use it. Who cares? Right? But at the same time, you're probably left going like, but that was an instruction. And we're overwriting an instruction with data? Can we do that? Yes. Should we? I don't know. But this is something we can do with the von Neumann architecture because data and instructions share the same memory space, so we can go and butcher our RAM all we want. We can do that. Should we? I don't know. If you are really put in a position where you have such limited space and you need to squeeze out everything you possibly can, maybe that's a great feature. But with that feature, also, I imagine you can appreciate has recipe for like disaster here, right? I'm seeing like the blank faces is throwing me off. I don't know if it's like because you're like, yeah, obviously I get it, or if it's because you have no idea what the hell I'm talking about. So I'm going to say it again. Instead of saving to C, or even F, like I was saying, we could overwrite this data because I didn't need it anymore. I could overwrite the contents of address 0 because I didn't need it anymore. But that was an instruction. Here, I'm overwriting data. It's just data, but it was data that was given to the system before runtime. So it almost feels like it's like sacred, you know? Like this was given to it. If it was data that was like created at runtime and saved in RAM, it feels a little bit more like, I feel a bit more comfortable like writing it, right? But this was like given to it at like before runtime, meaning like, I don't know, it's got like, it feels a little bit more special, so maybe overwriting it feels a little yucky. I don't know, maybe. But I really think we can appreciate the fact that overwriting an instruction with data is really weird. Now, mind you, when I say overwriting an instruction with data, really all I'm doing is I'm overwriting zeros and ones with different zeros and ones. It's what does that bit pattern mean that's important here. But I don't know, it feels really weird, but we could do it. In fact, I could do something like, instead of storing into 0, why don't I say store into 0, 1, 2, 3? Overwrite yourself. Imagine that. I could do that though. I've already fetched the instruction. I don't need it anymore. So overwrite the contents of this address, the one that just said output, with the data. Is it clear what I'm saying? I just got the instruction. It's like you're running along like a, I don't know, never mind. What if I did something like this though? What if I said like, okay, save into, okay, 0, 1, 2, 3, 4. What if I said save into 4? Would that be a good idea? Probably not. Because suddenly I change the contents of, like I change what the computer is going to think is the next instruction. Okay, halting. Okay, consider the program before improving the required clock cycles RAM. Okay, what would happen if the halt instruction was not included? Just look at this here. There's a halt. Right here. But imagine there was no halt there. I just put 0, 0. What would the system do? Well, there's no trick to it. It would fetch the next instruction. What's the next instruction? Halt. Okay. Man, is the next instruction halt? I just overwrote halt with 0, 0. The next instruction is in fact no op. So it does no op 4 clock cycles. No op 4 clock cycles. No op 4 clock cycles. Or actually, what did I store? I stored something into here. I stored 63, which was 1F, which is interestingly, load the contents of, what is 63 in hex? 3F, right? Right? Because 64 would be 4 here. Yeah. Which, interestingly enough, we talked about this last time. Interestingly enough, the bit pattern for the number 63 and the bit pattern for the instruction load into register B from RAB address 15 is the same bit pattern, which is amusing. But suddenly we would get down to the data that we just saved in here. Remember, this is before optimization at all. So this was like the result of the addition was stored here. So the system would take that data, but that data would get put into it would get fetched, because the system never halted. That data would get fetched, so 3F would go to the instruction register. The instruction register would get decoded, or the contents of the instruction register would get decoded to mean, oh, load the contents of F into B. Now here, that wouldn't really break anything. That would just put 32 back into B, which is rather unnecessary here, but that's what would happen. And then down here, though, FF would be in there, right? Because FF is -1 in hex and also 255. So the next instruction would get fetched. But conveniently here, what does the instruction F mean? Halt. So it would actually stop. By dumb luck. By pure, sheer dumb luck. But let's say it didn't. It would suddenly get down to 1F, which would mean loaded to A, the contents of 32, okay. And then 2, 0, load into A, 0. It would treat all of these things as instructions. But it's not like it's like being nasty about it. It's just doing what it's told. It's fetch, interpret, fetch, interpret, fetch, interpret. It's going to fetch the contents of memory and interpret those zeros and ones as instructions because that's how the system is designed. So it's weird how, like again, and this is all a consequence of the fact that we have a shared memory for data and instructions. Is that good or bad? I don't know. But you might actually also kind of, this is just going over it. All right. So okay, let me make sure I'm not missing anything. However, the remaining memory address stored, 63, 1F0. Although we know the contents, it's data, the system does not know the difference. In the same way that the system didn't know, when I said int a, like the system doesn't know is an integer. It doesn't know if it's signed or unsigned. I, as the programmer, need to know that. And that affects how I write the program for my system. High-level languages might do a bunch of that heavy lifting for us in the compilation process, but we don't have that luxury right now. So we don't know the difference between, or the system doesn't know the difference between data and instructions. So the system would conclude that, like, well, that means load into B from RAM, halt. That's wrong. That should be an F. Oh, no, the contents of address D is halt. Load A from RAM and load D. But this is just pure dumb luck of what the data is. If I said add the numbers 1 and 2 together, I'd have very different results. If I said add the numbers 100 and 200 together, I'd have very different results. Like the binary patterns for the result of those things would mean very different instructions. The program would halt after hitting D, though, by pure luck. However, it should be clear that's something we need to be very mindful of. So when using the save A instruction, an effort was made to save to memory addresses away from instructions, keeping a separation between instructions and data. However, this is not a requirement, and any memory address could be used. We already talked about this a bit, right? Like when I saved, like here, 5 was save A to some RAM address. And I was saying, like, we could have put it here, we could have put it here, we could have put it here, we could put it here, we could put it here, we could put it wherever we want. If one wanted, they could write data to an address that stores an instruction, thereby overwriting it. This means that the program can actually modify its own code. Is that clear? The program can actually modify its own instructions. Like, imagine I actually had like an instruction that was like, this wouldn't quite work with our system, but maybe I can make a point here. Imagine I had an instruction that said like load a RAM in E. And then I wanted to load and then like stuff happens, right? But like if I could somehow maybe get back to that instruction, I don't mean a copy of that instruction, I mean that instruction in RAM, but somehow like add 1 to it. Because if I wanted to load into A the contents E, and then later load into A the contents of F, if I could actually add 1 to that instruction, even though it's an instruction, not data, if I could add 1, or maybe even more crazy, I actually want to do the instruction later, I want to do load B, that's D, B from RAM, F. I want to do that. This bit pattern is 0001 1110, and this bit pattern would be 0011 1111. So I actually have to add 1, 2, 4, 8, 16, 32 plus 1. If I could somehow add 31 to the bit pattern for this instruction, I get this instruction, and maybe I want that. Maybe I can like literally like hack my code. Like I can perform instructions, I can perform operations on my instructions to modify the code to do what I want. And maybe the thing I want isn't a good thing. Like what if I'm an asshole and I want to like really mess up your code? Like really mess up your system. I can do that though if I wanted, right? So I've asked this before. Who took 162 with me? Okay. Now, raise your hand if you, like, how long ago did you take it?
2 or 3 years ago.
2 or 3 years ago. Was it in Java or C?
Java.
Java. Okay, so you would have missed the boat. Did anyone take it with me longer ago than that? No, that's fine. Back then, when I did it in C++, and I was using Visual Studio for it, okay? And Visual Studio is an IDE. It's not the language, it's just a tool used and helps you write the code, okay? That's it. What I did in one of the labs when teaching people about pointers, I was showing them how you can actually go and do like pointer arithmetic. Like you could take RAM addresses and like add to them to get different RAM addresses, right? So for those of you that, who here's never used C++ before? Okay, you're lucky. It's not that bad. It's actually a lot of fun. I'm being silly. But like what's interesting about C++ and C and other languages is if I have like int a equals 55, okay? If I say, well, what's a? It gives me 55. But I could actually ask, and I might get this backwards, so if I get it backwards, forgive me. But I could actually no. Is it star or does the star go in front? I can't remember. I say, tell me what a, tell me like dereference that, no, not dereference, it's been a while. I'm not even getting the words right. Basically, I could say, I don't want a, I want you to tell me where is a? Tell me the memory address of a. So this might be like, oh, well, that's OX, FF, 1D, 2, F7, whatever. It's some giant number because we've got a lot of RAM. Okay? So another interesting thing is I can take a memory address. If I had somehow a memory address, I can then say, no, I don't want the memory address. Tell me what's in that, go in that memory address. So if I have a memory address called a pointer, so if I have like b int star b equals like, if this is a memory address, I could say like ampersand, oh my gosh. Is that an ampersand? No, that's an L. And B, that'll be like, oh, don't give me the memory address, go like in B. And I could say, okay, 7. And that would go to the memory address, but inside of it, put a 7 in there. So if you really wanted, I could take this plus 1 and then ampersand it. I could say, give me that memory address, add 1 to it, but what's in there? I don't know. Maybe it's something super important for your operating system. Maybe it's an instruction. Maybe it's some other data you just had. Maybe it's nonsense, it doesn't matter. But I don't know. I got the memory address of A, I added 1 to it. What's stored in there? Because remember, RAM is like, right? Think of it like a giant array. Some of the stuff in there is meaningful. Some of it's nonsense. Like it doesn't matter. So I say, go here, add 1. What's in here? I don't know. But open it up and modify it. Equals 17. Like go in there and modify it. I used to make students do this in 162 for fun to show them how you can really mess things up. Now, if you're doing this in Visual Studio, if you like try to do this code, Visual Studio goes, are you sure about this? You probably don't want to do this. This is very bad, right? But it's not because C++ is telling you not to. No, C++ entirely allows you to do that. Like what we can do with our system. We can go start screwing around with RAM a lot. Now, if you were to do this in another IDE or just a text editor and hit run, your computer would be like, okay, yeah, sure, you want to do that. But Visual Studio is being nice to be like, no, don't do this. Anyways, you can really mess things up. All right. Any last questions before we're done? No? All right, see you all later.